Modern AI is highly proficient at writing isolated code blocks, summarizing documents, and answering direct questions. But when you task these same models with managing deeply complex, interconnected software systems, that isolated proficiency fractures and collapses entirely. Solving this limitation is the primary hurdle for the future of automated software engineering and cybersecurity. To move beyond helpful chatbots, AI must be able to hold an entire digital ecosystem in its working memory. Previous flagship models functioned perfectly as standalone assistants. Give them a discrete task, and they execute it. But when you ask them to process massive, sprawling environments, they lose critical details and hallucinate connections that don't exist. The industry is currently bottlenecked by retention. While code generation has become a commodity, maintaining a high-fidelity map of multi-layered context remains the primary technical obstacle. We can see exactly what happens when an AI hits the ceiling by looking at a real-world engineering problem. In this case, an attempt to completely migrate a complex front-end user interface codebase away from its existing back-end infrastructure. The migration triggered cascading technical failures. Local port connections dropped entirely, image assets failed to load, and environment variables collapsed. To guide the AI, the engineers stepped in with exhaustive manual intervention. They fed the model isolated error logs, detailed the directory structure, and provided multiple screenshots to help it visualize the failing environment. This chart tracks the scale of that failed attempt using the previous state-of-the-art model, Claude Opus 4.8. It shows a massive spike reaching 3.4 million tokens consumed, measured against a flat line representing 0 successful code executions. Over a multi-day experiment, the engineer poured extreme computational resources and time into a single problem, only to end up exactly where they started. The root cause of this failure is structural. The AI's architecture simply cannot hold the complete map of the system in its working memory simultaneously. As it attempts to fix one file, it forgets the specific dependencies required by another. This specific migration failure outlines the hard capability ceiling of traditional generative AI architectures. Throwing raw compute power at a complex problem achieves nothing if the model's underlying reasoning architecture cannot process the scale of the information. Claude Fable 5 introduces a new architectural approach. It is designed specifically to ingest massive, interconnected datasets without losing resolution on the smallest details. This diagram visualizes the scale of Fable's working memory. It features a context window capable of holding 300,000 to 1 million tokens. This allows entire code repositories, chat logs, and historical states to be ingested into a single processing core simultaneously. Because the data is held in memory, the model actively builds connections, mapping peripheral details and dependencies across the project. Fable 5 also introduces a new core parameter, dynamic effort. As this gauge shows, users can manually scale the computational effort level. Pushing the effort to settings like ultracode extends the processing timeline, delaying the output generation phase to prioritize deep logical routing. By scaling this effort, the AI is forced to spend significantly more compute time on multi-step reasoning before it returns an answer. Fable 5 trades immediate generation speed for the ability to reason through an environment, acting more like an independent agent than a conversational tool. Through an initiative called Project Glasswing, Anthropic developed a raw, unrestricted enterprise twin to Fable 5, named Mythos 5. Access to Mythos 5 is strictly ring-fenced to major tech partners like AWS, Apple, and Google. This restriction exists because the model possesses the capacity to execute, or defend against, severe cybersecurity attacks at a structural level. Returning to our unresolved UI migration problem, the engineer took the massive data context that broke Opus 4.8 and fed it directly into Fable 5. Fable 5 parsed the entire environment, identified the exact routing errors that the previous model missed, and deployed the necessary architectural fixes across multiple files. The previously failing UI variations loaded perfectly on the correct local port, scheduling features activated, and the entire asset library connected without error. By resolving a system-wide failure in a single execution, Fable 5 demonstrates the potential for AI to manage end-to-end technical migrations, rather than simply assisting with isolated subtasks. This success marks a transition toward AI systems that handle system-level execution. This movement points toward models capable of managing complex, high-stakes technical environments. But utilizing this level of intelligence introduces severe economic limitations. This chart compares token consumption rates. Fable 5 consumes double the output tokens of Opus 4.8, draining user usage limits at a high rate and driving up the hard cost of every prompt. There is also a strict temporal limitation. Fable 5 is not a permanent fixture. It is a highly restricted preview, scheduled to be taken offline on June 22nd. The complexity wall has been breached. The primary bottleneck for future development has shifted to the massive economic cost of the compute required to achieve this level of performance.